So let me just recall the original Hilbert 10th problem. So that was the decision problem where you have a polynomial with integer coefficients and many variables. And the task is given an input to decide whether there's an integer solution to the equation. But today we're going to be replacing z by analogous rings in number fields. And so let me just recall what the ring of integers of a number field is. Yeah. By the way, all fields today are there's no field except a number field today. So every field is a finite extension of Q. And so here's some number fields. And here are the rings of integers. And then in general, so these are supposed to be analogs of z. And in general, the definition of the ring of integers is the set of elements in the number field such that it's a root. It's integral over z, meaning that it's a root of a monic polynomial. Yeah, with integer coefficients. So for example, 1 plus square root of 5 over 2 is the root of x squared minus x minus 1. Okay, so so that's how we define it. So that's going to be some ring that's finite as a module over z. Okay, and so now what we want to do is take a piece of colored chalk and change z to OK everywhere here to get a new problem. So so this is going to be OK. Yeah, so I'm thinking of now fixing a number field and ask the analogous question of Hilbert's 10th problem over that ring instead of over z. And so now it's a new question, and the question is it still undecidable? I mean, I think everybody expected that it would be undecidable because it's pretty much almost every other statement about z had some kind of analog for rings of integers. So so in order to answer these kind of questions, it's going to be helpful to have the analog of the notion of a Diophantine set. So now we're going to be talking about subsets of OK instead of subsets of integers, and it'll be called Diophantine over OK or OK Diophantine. So that's if, well, the same definition as before. You have a polynomial depending on where you view one of the variables as a parameter. And what you do is you substitute a particular value. You look at it for the first variable, and then you ask, is there a solution in the remaining ones? So is there a solution to the equation Pax equals 0? And then the answer depends on A, and so you take the set of A for a good parameter values for which there's a solution. And then if it's any set that arises that way from some polynomial, it is called an OK Diophantine set. Okay, so there exists a P such that. All right, so there's also, I don't think I mentioned this the other day, but there's also a geometric way of expressing this definition, where you look in n plus 1 dimensional space, where you have the t variable here and all the other variables are sitting on that there, and then you take the hypersurface defined by this polynomial, and then you take the integral points on that. So so maybe these are the OK points. So these are the solutions to the equation Ptx equals 0 with coordinates in OK. And then you project them down to project them onto the t-axis. You take their t-coordinates. Okay, so and then those points that's going to be the set A. That's the set of t-coordinates for which there exists an x-coordinate that puts the t comma x makes t comma x the solution to the equation. Okay, so So all right. So let's see. So okay. So one thing I want to So what I want to take now is the conjecture of Demet and Lipschitz. So this is the conjecture. Yeah, so this is made, okay, so I'll just call it DL from now on. And this is from 1978. So what they conjectured is that Z as a subset of OK is dimension. And the reason they made this conjecture is that, well, this conjecture will imply that Hilbert imply that the conjecture is that this Hilbert sense problem over OK is undecidable, has a negative answer for every k. Yeah, I should say this is for there's a separate. This is a separate statement for every number to k, and same here. So the claim is that it's true for every k. Okay, so let me explain why this conjecture implies this one. So the proof here is, so we're assuming it's diapentine, and then the idea is to reduce this problem to show that this problem is at least as hard as the originally Hilbert sense problem. And so if it's harder than something that's undecidable, then it's also undecidable. Yeah, so in order to prove that this is harder, I want to show that it can encode each instance of the original Hilbert sense problem in the Hilbert sense problem over OK. So suppose you have an instance of the original Hilbert sense problem. So that means you have a polynomial with integer coefficients, and you want to so you want to express the existence of a solution in terms of equations over OK. And the way you do this is you look at, you take a system of equations. So this is going to be true if and only if the system where the first equation is the same as before, but now on this side of these variables are now supposed to be ranging over OK. So I need to put some extra equations to force the variables to take integer values. But we can do that if Z is OK diapentine, because you take the PTX that shows that Z is diapentine, and you use that equation many times to force each of these variables to be an integer. So you introduce some auxiliary variables. This is a whole tuple of variables, yeah? And then you have an independent tuple of variables down to xm. And then, so you have this system, and the point is, if you have an OK solution here, then these equations force the values of t1. If this one forces t1 to be in Z, and this one forces tm to be in Z, and then this gives you an integer solution to this. Yeah. Okay. So this should be clear. And then. Well, then if you want to, you can, as with equations over the integers, over the integers you use sum of squares to combine a single equation into one. And you can do something similar here. You can't use sum of squares necessarily, because a sum of squares in a ring of it, like a sum of squares in Q join I could be 0. But there you can use other quadratic forms to combine two equations into one, and then you can repeat. So you can combine this into one equation. And so this method lets you encode each instance of Hilbert sense problem as a special case of Hilbert sense problem over OK. And so overall, this shows that the whole problem is of Hilbert sense problem over Z. Maybe I should put this for emphasis. Is a subproblem of. It's encoded as special cases of this problem. And so as I said, this problem is more general, so it has to be at least as hard as that one. So yeah. Okay, so H10 over, yeah, and then he's saying, and we know that H10 over Z is undecidable. So So 10 over, okay. Is also okay, but again, all this relies on knowing. I mean, in order to do this reduction, you really need to prove that z is okay dipendent. All right. So the rest of today is going to be talking about this statement, proving that z is okay. Okay. Is there a question here? Oh, okay. All right. Okay. Well, maybe it's not good, but anyway, it's okay. Okay, no pun intended. Oh, this reminds me of a talk. I was once at MSRI, and I think Paul Voito was giving a talk, and he's talking about okay, and then I think he was giving a talk, and then somebody in the front row, I think it was maybe Zoe Chutsu, she said, I mean, I think he had written okay, but he meant to write OKS, like a ring of S integers. So she said, so she sees in the front row, she says, OKS. But Paul Voita somehow heard what OKS is saying, who cares? Yes. And so, anyway, so there's a moment of confusion, but it got sorted out. All right, anyway, I don't think I'm going to be talking about OKS, so we shouldn't have this problem today. All right. Okay, so, well, there's news from this year. As you may know, the Lipschitz conjecture has been proved. And so I want to, just in the past year, and so I want to say how this goes. So, and this relies on the work of a lot of people. So I'll break up the proof into four steps, 4 ingredients. So the first one is Deneff's result from 1980, which builds on. Maybe I should say, Deneff and Lipschitz, they already in their paper, they proved some cases of this. They proved it, for example, they proved it for all, actually Deneff already, even earlier, proved it for something, but they proved it for a bunch of, like quadratic extensions and some other kind of fields. And Deneff in 1980, he proved that it's true whenever E is totally real. So E is a number field. And if you assume it's totally real, which is the same as saying that it's generated over Q by one element, so it means it's isomorphic to an extension like this, generated by the image of X. And where the minimal polynomial of that element, which is going to be this f of X, where it has all, if you look at all its roots in the complex numbers, all the roots are actually real. Okay, so for example, Q adjoins square root of 5 would be an example because you could take f to be then x squared minus 5, whose roots are all real. All right, so that's the hypothesis, and then the conclusion is that the DL conjecture holds in that case. So in other words, Z is OE dipendent. Okay, so in other words, DL holds for this field. All right, so that's the first ingredient. So maybe I'll say a little bit. I'll say more about the proofs later. I just want to get all the statements on the board right now. So the second ingredient relies on a particular hypothesis that depending on a finite extension of number fields. So given a finite extension, you can consider the following condition. Which is okay. So I'll call it A sub k comma L. So, and what this means is the condition is that there should exist an abelian variety. So there should be an abelian variety over the smaller field, such that if you look at the group of rational points, so, and this group, by the Mordell-Weil theorem, this is always a finitely generated abelian group. So you can talk about its rank. And so the condition is that the rank should be positive, which is the same as saying that it's an infinite, that it's infinite. And then it should also keep the same rank. The rank should not go up when you look at the points over the larger field. Okay, so this is right now. This is just a condition. It might be true for pair fields or not. But what the theorem, what the statement now is, which was proved by Peter Stroimans and Carlo Pagano in 2024. And then maybe I should say, before I state the result, let me say also that there's also a second proof now. 2 months later.
Excuse me, raise the board, please.
Sorry, raise the board? Yeah, I mean, you can also raise yourself. But I can raise the board, yeah. Yeah, okay. Yeah, I don't mind at all if people are like bouncing up and down in the back of the room when I'm talking. So, okay. No, I can try to raise the board though. So, okay, so Levent, Alparga, Mandel Bargava, Leho, and Ari Schmidman. So they have a defense. And I mean, I think they were working on the problem around the same time as these people, but I think they finished it first. But okay. And then now there's also a third proof. I think about 6 months later, by David Zvina. Yeah, and so I didn't say what the statement was yet. Okay, so what did all these people prove? They proved that for a quadratic extension, if L over K is a quadratic extension of number fields, then this hypothesis holds. Then you can actually build such an abelian variety. And actually, Clemens and Pagano they showed you could actually take an elliptic curve that worked here. And same with Zvina. These other four authors constructed only an abelian variety, but we'll see that even an abelian variety is sufficient to work on that.
Okay. Extra conditions, then they add some K.
Yeah. So there's some extra. Yeah, I'm lying a little bit here. So you're right. I meant to say this. Yeah. So they had it. You're right. They had an additional hypothesis. They needed L to be Gallo over Q, and they needed K to contain a certain number of square roots. But it turned out to be not to be. I mean, it doesn't matter for the application. So, but yeah, I should write this. Maybe. Yeah. Okay. I think this is a time for the invisible color. So, okay, so this is, yeah, plus, okay, got it, okay. All right. Yeah, okay. So, good. Okay, so, so then the third ingredient is, well, I mean, what good is knowing that AKL holds? Well, it implies something. So this is, yeah, maybe I should say the source, where this came up is people were trying to generalize Matiyasevich's argument. I mean, that's the natural thing to try. If you already have a proof for Z, why not try to just copy it for the rings of integers? But Matiyasevich used, as I explained on Monday, he uses Pell equations. And he used in particular that the Pell equations have a rank 1 group of solutions. And in order to have, I mean, you can still look at Pell equations or analogous things like that, but they don't always have the correct And for higher number fields, they don't always have rank 1, and they don't have the right conditions. And so, I mean, they do satisfy enough in the case where you have your base field is totally real. In fact, that's what Denef used. But if you're over a number field which is more complicated, where it doesn't work that way, then the idea was to replace the Pell equation, which is like the group of units of a number field, replace it by some other finely generated group, like the group of rational points of an elliptic curve. And so the question was then, but in order to make that argument work, the analog of what Matiyasevich does, you needed some conditions on the ranks of those elliptic curves, and that's why this condition is going to be useful. And so so the details of so I proved an analog where I needed, if I could construct an elliptic curve where this rank was 1 and it stayed rank 1, then that would be sufficient. And then this was generalized by a bunch of people. So around the same time as me, I think independently, these authors, Cornelison, Thanasis Fedas, and Zahidi, they proved they could use some combination of elliptic curves and abelian varieties. And Schlappentalk and I independently showed that you actually didn't need rank 1. If you had an elliptic curve that satisfied this, that would be good enough. And then the most general version is in a very recent paper by Maser, Rubin, and Schlappentalk. Okay, I guess some people's names are just too long, I guess, to abbreviate. All right, so they prove the most general result, that even if you just had any abelian variety that satisfied it. And this statement is that if you have this, if you can construct this abelian variety, then what you get is that you have a way to show that OK is dimensioning into OL. Now, it's not quite as good as you would want, because you want to go, this lets you go down from OL to OK, but the conjecture is you can go all the way down from the ring of integers all the way down to Z. And so, well, you could hope that you could maybe do this in one step. Like take K equal Q. And if you could go down from any L to Q, if you could satisfy this condition, then then combined with this, that would finish the problem. But it turns out that's not so easy. It's not so easy constructing these abelian varieties. So so unfortunately, it turns out you don't need to do all that. So okay, maybe I'll write it out this time. Okay, so Schlappentalk found a clever trick that where you don't need to know this for all. You don't need to know this for Q. You don't have to do it in one step. You can sort of build on knowing this for several pairs of quadratic fields, and then get all the way down. So so this is okay. So this reduction argument. I think she worked it out many years ago, but it was first published in this paper by Maser, Rubin, and Schlappentalk. Okay, so what this says is that if you have if you know two things, first of all, if you know Denef's result, so if you know that Z is OE diphantine for all totally real E, and you also know that OK is OL diphantine whenever it's the degree 2 extension. Yeah, so if you have those, then you can conclude that Z is OF diphantine for all F. Okay, so that last thing is, so this last thing is just this is just the full Denef-Lipschitz.
'Lipschitz conjecture. What's that?
'Lipschitz conjecture. 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 'Lip For all, which, for all F?
For any number field F. Oh, okay.
Yeah, every field is a number field. There's no such thing as a field that's not a number field today. So yeah.
Why is one and why do you write if this result that is known holds?
Oh, because yeah, it's known. I'm just saying I'm just trying to break up the argument into 4 steps. And so, yeah, so you're right, this is known. And actually this is known as well. So I'm just saying that, with this modus ponens or something, if you know X and, so yeah, if you know X and you know X implies Y, so this is like the X implies Y.
So you're
And that's the X. What?
You're doing mathematics without modus ponens, and then at the end you will apply modus ponens.
Yeah, something like this, yeah. Somebody else have a question?
So point 2 was the bottleneck for a long time, is that right?
Yeah, well, that was the last one to be done, so, yeah. Yeah, it was I guess so. I mean, I guess, yeah, so, yeah. I mean, in fact, Clemens and Pagano construct elliptic curves, so I guess since 2008, it was a bottleneck, so, yeah.
So you can always take a elliptic curve, or sometimes you need to take a abelian variety of different dimensions.
So Clemens and Pagano prove that you can do elliptic curves, well, at least under this extra hypothesis, and actually Zwinian proves that you can do for all quadratic extensions, you can find elliptic curves. In fact, what Zwinian proves is actually not only can you make this hold, but you can actually make both of them have rank 1. Wow. Okay. So yeah. Okay. All right. So okay. Maybe I can just quickly. I mean, maybe it's obvious to you, but just to be completely explicit, let me just prove that. Okay. This is just logic, but okay. I guess you're all supposed to be experts in logic. So, let's just explain. Let's just explain that these 4 things actually imply DL. Yeah. Figure out just putting things together. So yeah. So I mean, well, first of all, 1 gives you hypothesis 1 in Schleppenthal's reduction, and then if you put 2 and 3 together, well, I guess you know how implications work. For every degree 2 extension, you know AKL, and you know that AKL implies that OK is L extension, then you get 2. Yeah, so this implies 2. And then Schleppenthal's reduction argument lets you combine these to get so this is you have 4, it gives you the brushes. Okay? All right, so all I have to do is prove these 4 things. So, okay, I don't have a whole lot to say about 1. So the next proof of 1. I mean, it's pretty complicated in the sense that, I mean, I think I mentioned this already. He uses Pell equations in a similar way. Let me just say, a la Matiyasevich. And it's kind of complicated in the same way that Matiyasevich's proof is complicated. So I'm not sure if I can fit it all in my head in one time. So, but anyway. Okay, so that's all I'll say about 1. And yes, but I think what I'll do next is sketch the proof of, or actually I can give the full proof of part 4. This is Schleppenthal's reduction. So why is it enough just to know these conditions for quadratic extensions and totally real extensions? Well, how do you combine totally real, knowing it for totally DL from totally real fields, and also knowing being able to go down by quadratic extensions only? How do you get all extensions from these? So this is a very nice trick. So the first claim is that if you have a finite extension, and of course these things are both number fields, so the finite extension, and you know that the Z is Diophantine in the bigger ring, so it's OF prime Diophantine. Then it's also Diophantine in the smaller ring. Okay, so how does this work? So the proof is, the idea is basically that if you have equations in f prime valued variables, you can write those, OF prime valued variables, then you can write those, you can express these in terms of, you can write this as a finite module over OF, and encode each variable here as a combination of variables valued in OF. So in order to do this, you use a finite presentation of this, of OF as a module. I'm tempted to say, choose a basis for OF prime as an OF module, but you can't always do that because this is not a PID and this thing is not always a free module. It's a projective module, it's close, it's still a finely generated module. And so you can choose a finite presentation. In other words, it's the module generated by some finite number of generators modulo some finite number of relations. And so you can choose a finite presentation of OF prime as an OF F module, and you do this in order to encode equations in OF prime valued variables as equations in some newly introduced variables. It's like, for example, if you're doing this for Z and Z adjoint I, you have an equation, you have some variables that are supposed to be valued in Z adjoint I, say x, you replace x by y plus iz. And then you expand everything out, and you take the real and imaginary parts, so you get a whole system of equations that's equivalent to the original one. In OF, so you valued variables. Okay, so then, so in particular, once you've done that, if Z is cut out, if Z can be cut out by equations over OF, in other words, if Z is Diophantine over OF prime, so then, so that's if this is true, then it can also be cut out by OF equations. Okay, so and the point of this claim is that it lets you do reduction. It means you can always, there's no harm in enlarging F. Because if you can solve the problem for the F prime, then you can solve the problem for F. So I want to, so this is the end of the proof of the claim. And so that's, so we may assume that the field F, by making it, you can replace F by its Galois closure over Q. So you can assume that F over Q is Galois. Okay, so that's the first part of Schopenhauer's reduction. Okay, any questions so far?
Excuse me, you said the proof of one used value equation that is complicated, but can you say a word why this kind of totally real extensions are as special?
Yeah, it's because when you look at the Appel equation over a number field, over the ring of integers of a number field, so that's related to the unit groups of quadratic extensions of that number field. And so what becomes relevant is what the rank of that group of units is. And there's a formula in general for a number field. If you look at the unit group, there's a formula for the rank of that group. And the formula is that it's R1 plus R2 minus 1, which is where R1 is the number of real places and R2 is the number of complex places, which are 1/2 of the number of, it's the number of complex conjugate pairs of the roots of the minimal polynomial. And so it's because that formula depends on how many of the embeddings are real and how many are complex. You need it to be totally real to get the correct rank conditions that you need. So yeah. I mean, later they were able to do it for almost totally real fields, where you just have one complex place. But yeah, that was done, I think, by Fedas and Floppentoff independently, I think. But yeah. Oh, I think I did. Yeah. Okay. So did I already? I don't think I did this yet. Right. Any other questions? Okay, so right, so we're in the middle of the proof of 4, yeah. So far I've said we can reduce to the case where f is Galois. So I'm going to assume f will be Galois from now on. Now, when you have a number field, you can look at all its complex embeddings, and some of them might land in the real numbers. But in any case, each time you embed this number field, this Galois number field, into the complex numbers, you can look at the complex conjugation. You have complex conjugation on the complex numbers, and that, okay, it restricts to, sorry, my sentence is going like this, okay, so it restricts to some automorphism of f. I mean, the reason that it maps f, the complex conjugation maps f to f, that's because f is Galois. And so, yeah, so you get for each embedding gives you a complex conjugation on f. And yeah, and then once you have that, you can look at the fixed field, which is kind of like the real part of f with respect to that embedding. So this is the notation for fixed field, and this just means it's the set of elements such that that are fixed by the complex conjugation. So it's like f intersected the reals for that embedding. But if you change the embedding, you'll get a different f sigma. Yeah, but in any case, for each of those embeddings, this extension by Galois theory, since you're taking the fixed field of a group of order 2, this extension will be a degree 2 extension. And so by hypothesis, you get that the ring of integers of the smaller field is dipentine in the larger field, in the big F. And this is by 2, by assumption 2. Okay, so and now what you can do is you can take the intersection. So we have f up here. Maybe I draw the diagram. So the idea is you have f, which is a big field over q, and then you have all these quadratic subfields f for all the different embeddings. And now what I want to do is take the intersection of them all. So, okay, so then, yeah, and then Q is way down here somewhere. And okay, so let E be the intersection over all sigma of this sort of index 2 subfield. And then, yeah. So then, well, what's the ring of integers? I mean, you can show that then the ring of integers, they're just the things that are integral over z in all of these things. So it's going to be the intersection of the rings of integers of these fields. But if you already know that each of these rings of integers is Diophantine OF, then, well, an intersection of Diophantine sets is also Diophantine. You can just put in more equations and combine them into one. So this is E, and then this is equal to this, which is, so this is also going to be OF Diophantine. So in other words, I mean, not only can we go down by these quadratic extensions, which was the hypothesis too, but now you can go all the way down from F to this field. And the good thing about that is that on the other hand, what kind of field is E? I mean, for every time you try to embed it, E into the complex numbers, it's going to land in the real numbers, because otherwise you would have another sigma that cut it down further. So on the other hand, E is totally real. And therefore, so that means that Z is, by assumption, that Z is OE Diophantine. So that's by assumption 1. Okay, so that means you can go down from F to E, and you can go down from E to Q. And there's a transitivity property that you can do. So, do you have a question?
Yeah. So so the intersection that defines E ranges over all sigma arising from restricting every embedding?
Yeah, that's right. You take all possible embeddings of F into the complex numbers, and then you intersect them all. And then the intersection, whenever you try to embed that intersection into the complex numbers, it has to land in the real numbers, because otherwise you could extend that embedding of E into C to some F into C. And so, yeah. So, okay, so if you use the transitivity property, so then by transitivity, which, I mean, I'm not explaining this, but it's just a purely formal thing, then you can first, I mean, in other words, what you do is you write down your equation over F, but you can put additional equations to force your variables to take values in OE. And then on those variables, you impose additional equations to force those OE value variables to actually take values in Z. And so in that way, you can show that Z is Diophantine. It's OF Diophantine. And that's what we're trying to, that was what we're trying to do. Okay, so that was Schappenhaug's argument. So so that's really nice, because now the only thing, well, if you've done one already, then the only thing left is to prove, that for these quadratic extensions, that you can go down for one quadratic extension. All right, so let's see. So the next thing I want to do is start explaining the proof of 3.
Sorry, can I just quickly ask?
Yeah.
So you know that the definitely like finite intersections of Diophantine sets is still definite, but like can you do it for infinite intersections?
No, well, it's only for finite intersections you can do it, but in this case it is a finite intersection, because there are only finitely many ways to embed a number field into C. Because first of all, every number field is by the primitive element theorem, it's generated by one element. So there's one way you can say it. So it looks like this. And then to give an embedding of this into the complex numbers, I mean Q has to go to Q, because integers have to go to integers. And so the only freedom in defining the embedding is to say where x goes. And x must go to, because f of x equals 0 in this ring, x must go to one of the roots of f. In fact, to give this embedding is equivalent to just choosing a root of f. So the number of embeddings is just the same as the number of roots of f, which is just the degree of this number field. And so it really is a fine intersection here. Yeah, that is important though. Okay, any other questions? Okay, so let me start. Okay, so I'm not going to be able to finish the proof of 3 today, but I just want to talk about some ingredients, and then I'll talk more about it on. Yeah, this is supposed to be a 2-part talk, so the next part I'll finish it tomorrow. So all right, so just to simplify notation a little bit, let R be one of these rings of integers, and so I don't think I'm going to use this today, but I just want to extend the notion of Diophantine set to sets of points on varieties or schemes. So okay, if you don't know what a fine type R scheme is, just think of it as being, it's kind of like an algebraic variety. It's just some geometric object, some algebraic geometry object that's defined by finitely many polynomial equations with coefficients in R. So that's all you should think about. So it's just given by some system of polynomial equations. So that's more or less what this is. And then I want to talk about a subset. So before I had subsets of OK being Diophantine, but now I want to talk about subsets of the points of this scheme. So when I write x of R, if you're thinking of the x as being defined by some system of polynomial equations, this is just the set of solutions to those equations, where the coordinates are, where every coordinate is in R. Okay, so those are the R valued points of this scheme, and then A is going to be just some arbitrary subset there, and then the definition I want to make is that A is Diophantine over this ring, so R Diophantine if A arises as the image of the R points coming from some other fine type R scheme that's mapping down to X. So I mean, you should be reminded of the picture I drew earlier today, where I don't know if you remember. I had this hypersurface, and I said that if you took the integer points, the OF points on that hypersurface, and you project them down onto the T coordinate, then the set you get that way is OF Diophantine. And so this is just a natural generalization where now you take the bottom doesn't have to be the affine line anymore, it could be any variety. And also the thing that used to be a hypersurface, it could be any other variety or fine type scheme. Yeah? Okay, so that's
the F.
Oh, sorry. This is this map. Yeah. So it's this morphism. So I just mean you take. I just mean you take the R points here and you take their image. Yeah. And that F stands for finite. Okay. Yeah. All right. So good. Thanks. All right. So and maybe make one remark. So with a little bit of work, I mean it's not completely obvious, but you can show that when X is just the affine line, this new notion of Diophantine for subsets of A1 of R, then it agrees with the previous notion for subsets of R. Yeah. So I'm not changing the definition for subsets of R. Okay, anyway, let me, don't worry about this for a while. I'm probably not going to use this for a little while until tomorrow. But, Yeah, so, okay, get this part belongs there too. Okay, so let's just put it in a bubble and just send this bubble one day into the future. And we'll use it tomorrow. Okay, let me now prove some other things. So, I mean, I have to build up, in order to prove this statement 3, I mean, eventually I want to get that OK is OL diphantine for this quadratic extension. But for now, let me just prove a bunch of, I mean, I have to do a lot of work building up diphantine subsets, building up a library of diphantine subsets in order that I can use to build new ones. And so let me just get started with this. And so the first thing is the lemma of definable Lipschitz that says, okay, so that if I is a non-zero ideal, so this is just going to be some statement of algebraic number theory. Non-zero ideal. Then there exists an element of the ring of integers that satisfies this congruence. Okay, and I'll explain in a second why I want this, or why Denef and Lipschitz wanted this. So, but let me first just prove this. Okay, so the statement's clear, yeah? So I claim that I can always solve a congruence like this. I mean, yeah. So I mean, if you want, you can just think about. I mean, it's actually interesting even when. Well, it's not very going to be hard, but you can just think about this being z. I mean, suppose you want to say, I'm claiming that for any integer, for example, you can, if I want mod 100, I can find an integer x that satisfies this congruence. So how do you do this? So first, let's first do the case where I is a prime power. So suppose that I is p to the n for some prime ideal of OK. And let's assume that prime is not above 2. It's not a prime divisor of 2. So then what do? How do you solve this equation? Well, if the prime doesn't divide 2, that means that 2, the image of 2 in this residue ring, is going to be a unit. And so that means it has an inverse modulo I. And so then you can just let then you can just let x be anything that reduces to the inverse of 2. The inverse to the inverse of 2. In this ring, yeah. So that's how. That solves the problem. I mean, that makes this factor equal to 0. So it means the whole congruence whole. And so okay, that's the first case. Maybe I should have called that case 2 because the next one's going to involve 3. Yeah. All right. Let's do that. Okay. Let's make it case 2. And then case 3 is where I is again a prime power, but this time the prime doesn't divide 3. And then you do the same thing, yeah. Okay, dot thing. And it's great, I mean, if you combine these, if you give me a prime, it either doesn't divide 2 or it doesn't divide 3. So that covers all the prime powers. These two together. And so now I can do case 1, which is the general case. Okay, so maybe I'll just call it general case. So we know how to solve this. We know how to solve this congruence for prime powers. And you can probably guess what I'm going to do now. You can just use the Chinese remainder theorem to piece together those prime power solutions for any ideal. So yeah, so you just use the Chinese remainder theorem. So you find a solution modulo each prime power divisor of I, and then you use Chinese remainder theorem to put them together to solve all the congruences simultaneously. Okay, and now so now why did Denef and Lipschitz want to prove this? So it's because Well, they were trying to show that the property of being non-zero is Diophantine, which is not an obvious thing. I mean, because you can't just say that something is non-zero if it has an inverse, because the inverse, because we're talking about equations over not a field, we're talking about equations over a ring of integers. So it's not immediate. It's not. I mean, over a field, it's obvious that the non-zero elements form a Diophantine set, but over a ring of integers, it's not so clear. Actually, I'm wondering, maybe somebody knows. I mean, I have a feeling that this argument that I just gave, probably somebody did this over Z long ago, but I just don't know the history. Does anybody happen to know? I mean, it sounds like it just feels like the kind of thing that Julia Robinson would have figured out, or something like that. Okay, anyway, so okay, so yeah, so the corollary of this is just that if you take the non-zero elements in OK, then that's a Diophantine set. And so to do this, let me just show you so the proof is you take that lemma and you take I to be the principal ideal generated by a non-zero element. And then if you want to express the fact that an element of OK is not zero, using the lemma, you can see that this is going to be equivalent to saying that there exists x and y such that 2x minus 1, 3x minus 1 is equal to y times a. Yeah? I mean, certainly, if you have x and y that satisfy this, and the left-hand side is not zero, so that's going to force a to be not zero. Yeah? So if you have a solution to this, then a has to be non-zero. Conversely, if a is not zero, then according to that lemma, you can find x such that 2x minus 1, 3x minus 1 is congruent to 0 mod a, which is the same thing as saying that it's y times a for some y. Okay, so that's that proof. And the reason that this corollary is useful because now I can secretly talk about elements of the fraction field of OK using just equations with OK valued variables. Because I can represent any element. Well, in the obvious way that you deal with the fraction field, you write the elements as fractions. So you write the elements as A over B. So here the A and B are. So these are elements of OK. But the point is, we now know how to say that B is not zero. So using this corollary, so you can do this, and so using this, we may so first of all, you can use k-valued variables in OK Diophantine definitions. When you're trying to define OK Diophantine subsets, you can use k-value variables by encoding them as pairs of OK elements and so on, and writing down the corresponding equations. And you can also talk about subsets. You can talk about OK, what it means for a subset of of x of k. So you can talk about k-value points for a finite type k scheme x, and you can encode those using OK value variables and equations. All right, so I'm almost out of time, but let me just finish by just taking care of mostly bookkeeping, some easy statements about ideals. So how can you encode an ideal? I mean, not every ideal is principal, so I can't just say it's just the ideal generated by one element. But there is a fact about Dedekind rings that every ideal is generated by two elements. So you can always encode an ideal just by a pair of elements. So you can just have the ideal generated by two numbers for some I1, I2, okay. And then given once you have that way of encoding ideals, you can express lots of things in Diophantine terms. For example, suppose you want to say that a third element belongs to this ideal. How do you do that? Well, just by definition, essentially, it means that there exists x and y such that A is xi1 plus yi2. And if you want to say that one ideal divides another one, I mean, that's the same as saying that I is contained in J. So that just means that both of the generators lie in J. And then you can expand this out using the previous pull. And then, how do you say that I equals J? If you have two ideals, that's just the same as saying that I divides J and J divides I. Okay, and how do you say that I and J are co-primed? Well, co-priming just means that I plus J is the unit ideal. So that's the same as saying that there exists an I, and there exists a J and J, such that I plus J is equal to 1. And, okay, I mean, you can keep going like this. So maybe we'll do a few more things. So if you have a fraction in K, how do you talk about the principal ideal? Or how do you, so if this is true, then how do you express the fact that this ideal is a ratio of these integral ideals? That's just the same as saying that A times J equals B times I, which you can express using this one, and so on. And, okay, how do you talk about the, well, I mean, if you have an element of K, you can't always write it in lowest terms because we're not in a PID, so you can't talk about the GCD as an element, but there is a GCD as an ideal. And so you can always write the ideal generated by S as a fraction where I and J are co-primed. And so and then the top one is called the numerator ideal. And so this just means that there exists an ideal such that S is equal to I over J and IJ are co-primed. So you can detect numerators. Okay, and then maybe last one. You say, okay, this is a really trivial one. You want to say that A is congruent to B mod I, that's, well, just essentially by definition, and that just means that A minus B is an I. And so you can use the first bullet up there. Okay, so I'm going to use all these ingredients next time. So let me stop here. Yeah.